Hello and welcome to today's session. My name is Paul and I'm a Senior Cloud Solutions Architect here at Microsoft. I'm joined today by Callum White, a Microsoft MVP at Bump Digital. We're both really excited to be here today to tell you about some recent build announcements that are related to containers, serverless and API management on Azure. We're going to jump straight in and we're going to start off with some recent updates to the Azure Kubernetes service. So we tend to find that customers adopt Kubernetes because of its flexibility, scalability, portability, and of course because of its broad ecosystem. And the Azure Kubernetes service, or AKS, preserves these attributes and it builds on top of them. And we want to make AKS the most advanced Kubernetes platform available to customers. And to do this, we focus on four key areas. First, we make it easier for developers to be productive and focus on their applications. Second, we provide best practice recommendations, but allow the choice and flexibility for customers to choose the tools that they're most familiar with. Third, we provide a secure, managed Kubernetes service with add-ons like managed add-ons and managed nodes. And we provide a resilient and scalable platform so that customers can confidently run their mission-critical apps on Azure. And Azure is the only cloud that brings together capabilities for modern app development, open source innovation, cloud scale data, and AI, all in one place. And we're using Kubernetes and AKS a lot here at Microsoft ourselves. Working with the teams that run Bing, Office 365, Teams, Xbox Online Services, and GitHub Copilot have really helped us understand the requirements of enterprise apps running on Kubernetes at really large scale. And by working with these teams, we've learned a number of best practices that help our customers be successful by avoiding making the mistakes that others have made in the past, and they have also helped make an AKS a more reliable and more performant platform. However, there are still some challenges when customers look at adopting Kubernetes. First of all, there are so many options that the choice can be overwhelming. With so many options available, the learning curve can be steep. There's lots of documentation to read, there's lots of projects to evaluate and plugins to analyze. And so it can take a while to figure out what you want and need out of your platform. And whilst it's great that platforms like AKS have built-in capabilities to make some of these things easier, if you're not using them, then they're not really providing you any value. We also see that customers find it hard to find people with the right Kubernetes-related skills and expertise. These people are in high demand, and finding the right person at the right time for your project can be challenging. And even when you do find these people, ramping them up or ramping up new employees in general can be hard. They have to learn these Kubernetes skills, which they may not be familiar with. You also need to onboard them into things like your development and build environments and make them familiar with your DevOps processes. So we think that things can be easier here. What if your customers came pre-configured with the best practices that I talked about earlier? What if things like scaling and upgrades were automatically configured when you created a cluster? What if there were robust policy settings and safeguards that were enabled by default? And what if you could quickly and easily go from code to production-ready Kubernetes deployments? So today I'm going to show you how you can have all of these things while retaining the flexibility and extensibility of Kubernetes. In the demos today, we're going to be looking at a simple three-tier architecture which is a microservice-based pet store application. We have two front-end services representing or being used by the two main types of users that will interact with our pet store. We have four back-end services, which the front-end services interact with in a combination of different ways. We have a couple of data storage services for storing things like product information and order status. And we also integrate with a number of AI services too. So let's have a look at how we might deploy one of these microservices into AKS in a new and different way. Now, before I show you the demo, I want to quickly introduce AKS Automatic. This is a new experience for AKS that makes it even more productive for developers and platform teams, especially those without previous platform engineering experience. And this is a new experience for AKS, which makes the most common tasks fast and frictionless, as I hope you'll see during the demo. But it also preserves the flexibility, extensibility, and the consistency of Kubernetes, which makes it the ideal option for hosting your modern and AI applications. Now, typically, we see that dev and ops best practices have high learning curves, but within AKS, these best practices have been formalized within the product. And we've harnessed experience and expertise that we ourselves have accumulated by running some of the largest and most advanced Kubernetes and AI applications in the world, Office 365, GitHub Copilot, and so on, as I mentioned earlier. And this new experience automates everything to be production ready right out of the box, from cluster setup to cluster updates and management, from performance to security safeguards and policies. And it means that the developers can go from code to Kubernetes in just a few minutes. So let's have a quick look at a demo. So here we have a GitHub organization. And within this organization, we have a number of repositories which correlate to the microservices that we will be running. And if we look inside one of these microservices, the product service in this case, we'll see that we've got a fairly standard Rust application. We've got things like API routes to make the application function in the way we expect. Now, we want to deploy this application into an AKS cluster, but we don't have any AKS or Kubernetes experience. So in the past, this would have meant reading documentation and trying to figure out the best way to do this and hope we don't make too many mistakes along the way. But if we look in our Kubernetes service blade in the Azure portal, we can see there's this new option to deploy application on AKS Automatic. And when we select this option, it launches a new wizard. And if you've ever deployed an AKS cluster before, you'll see that there's a lot, this is different to normal. Now, the first thing that this wizard asks is for access to your GitHub repository. And once it has that access, it can then view your organizations and your repositories. So we'll select the relevant repository and the branch that we want to build from. We'll also give this workflow that we're setting up a name that's a human-friendly name that makes it easy for us to understand what it's doing. The wizard has gone out and analyzed that repository, and it sees that we're running Rust. It suggested a port we might be running our application on, but we need to change this because we're running on a different port. And it's generated two files here, the Docker file and the Docker ignore file. And we'll mention those again in a minute. It's also creating a container registry. We're going to change the name here just to give this a more human-friendly name again. We're going to set the region that we're deploying into, which is the UK South region in this case. And we're just going to change the name of the image. So this is the name that the container image will be given when it gets pushed up into this container registry. And we'll set this to match the name of the service because that makes sense. We can then click onto the deployment details and we can define the namespace that we're going to be deploying this application into inside the cluster. And we can see that the wizard has again created two more files, in this case, deployment YAML and service.yaml. These are Kubernetes manifest files to help deploy the application. And now finally, we get on to cluster details. But if you have ever deployed an AKS cluster before, you'll know that normally you have a lot more configuration options here. All we need to do is set the resource group and the region, and we're done. We can then review our deployment and then go ahead and deploy it. And in the background, AKS is now deploying this AKS automatic cluster, a container registry. It's going to create the namespace within the registry, within the cluster, and it's also going to do a few other things like set up a GitHub action pipeline in our repository and create a pull request with those 4 files that it generated for us earlier. Once the deployment's complete, we can go ahead and click the Approve Pull Request button, and this will launch us out into GitHub. It will take us straight to the pull request. You can see there are 4 files that are changed. We could review these, but we're just going to go ahead and deploy, merge this change quickly. And this will start off our CI/CD pipeline, or the action that we generated. If we have a look in the action, we can see it's already running, and inside we have 2 jobs. The first is build image, which uses Docker build to build the application container based on the Docker file that was generated for us earlier, and then it will push the container image into the registry. And then the deploy job will take those Kubernetes manifests and deploy into our cluster. Coming back to the Azure portal, we can see our automatic cluster has now been created. And if we click through, we can then drill down into resources in the cluster, things like the services and ingresses that are. We can then filter by namespace and select the pet store namespace that we created as part of that deployment wizard. And we'll see a load balancer service with an external IP address. And if we click on external IP address, we get a response that shows that our API backend service is running. It's not pretty, but it's responding with application data. So what we've seen here is that we've gone from a code repository to an application running in an AKS cluster. The code repository didn't have a Docker file. It didn't have any Kubernetes YAML manifests in it. And we didn't have to run any Docker build commands to generate our container image, or we didn't have to push any images to container registries. We didn't have to have any experience of creating or running or operating or configuring a Kubernetes cluster. And we didn't have to write a deployment or a service manifest to define our application in Kubernetes language. And we didn't have to use any tools like kubectl to deploy the application into our cluster. So this is a really powerful new way for developers to deploy their applications into production-ready AKS clusters. Now, in the background, some of my developers have deployed a few more microservices to provide a nice, pretty front end. And if we go back to our Azure portal from this, we can have a look at another one of our ingresses, the storefront ingress. If we click on this YAML link, we can see the live configuration of the service that's running pulled from the cluster directly. And as we browse down through this YAML, we see this TLS section, and we don't really understand what this means. So we can highlight the text, and then we can use Copilot to explain what this means. And after a few moments, Copilot will come back with an explanation, and it will show that first of all, it will note that it's only explaining the section that we've already highlighted. So that's useful. It's not going to explain the whole YAML. And then it will run through each of the parameters. So it says the TLS section is for defining TLS settings. The host section will define the host names that are covered. And the secret name is the secret that defines the TLS certificate. But it goes on to add that in the context of AKS, the secret is likely to be a reference to a certificate that's stored in an Azure Key Vault, which is indeed the case in this architecture. So that's pretty cool. Now I'm happy to announce the public preview launch of a new feature called Service Connector, plus the integration of Service Connector into AKS and AKS Automatic. Now, workloads running on AKS clusters often need to access Azure backing resources, things like Key Vaults, databases, or AI services like OpenAI. Now, in the past, users have had to manually configure things like workload identities and secure networking connections to configure the secure access to these protected resources. But Service Connector greatly simplifies the connection configuration experience for workloads running in AKS. It takes care of the secure authentication and the secure network configurations, and it does so following Azure best practices. And this allows you to focus on your application code without worrying about your infrastructure, connectivity, or security. So let's have a look at Service Connector that's been deployed for our application. Now, if we expand our Service Connector, we can see there's a couple of parameters that are associated with it. Things like the endpoint of our OpenAI service that the application will connect to. If we select the service connector, we can click this YAML snippet button, and this will generate a boilerplate YAML service definition. And you can see these lines highlighted in yellow are the configuration options specific for the service connector. But if we change the resource type to Kubernetes workload, we can select services that are actually running in our cluster. And as we scroll down the list, we can see these same service connector configuration lines are also now in this YAML, and they're again highlighted in yellow. So we could take these, we could integrate them into our YAML files, and then we could apply them to the cluster. But there's this apply button down at the bottom. So this is the really cool part. We can apply the change live. And AKS has now gone and applied that change live to our workload. And so if we switch back to our application, we're now in the admin portal and we're on the add product page. So here we're going to add a new product to our application, but using the service connector, we've now integrated AI. And so we can now use AI to generate a description about the application, about the product that we're adding, and also generate an image. And these are just coming from the product name and the keywords that we've defined. And so what we've seen here is that we've connected our application running in AKS to the OpenAI service using Service Connector. We've added intelligence into our application, albeit the back end, but still an important part of the app, using the AI service, or the OpenAI service, sorry. We used a ChatGPT 3.5 model to generate a product description from just a few keywords and the product name, and we used a DALL-E model to generate a product image from the same input. And all of this, all of the communication for this has taken place over a secure, authenticated private network connection, avoiding the need to expose any of our back-end resources to public networks. Now, I'm also happy to announce a public preview of the Azure App Configuration extension for AKS. And you just saw this working in that last demo. You can install and manage the Azure App Configuration Kubernetes provider on your AKS cluster, and this will allow you to centrally manage application settings and feature flags for your applications. And in the back end or in the background, it uses Kubernetes config maps and secrets for streamlined management. And this extension will allow you to update your application configurations without having to redeploy your apps. And this will allow you to iterate faster on your app features and roll them out with reduced downtime. This feature will also help you implement secure deployment practices with unchangeable configuration snapshots, which will provide an audit history of the different configurations that you've applied over time. It will also help seamlessly control feature rollouts, which will allow for safe and gradual feature deployment across your application estate. And it will drive continuous improvement and help elevate business value through robust experimentation features. Now, we expect that this will improve your overall efficiency by centralizing the management of your configuration data for all of the services across that are running in your AKS and Kubernetes estate. And now I'm going to hand over to Callum for a few slides to talk about the power of serverless architectures.
Fantastic. Thanks, Paul. So serverless, what is serverless? I think we should start with that. So serverless, of course, abstracts away a lot of the underlying infrastructure and makes it far more seamless to run applications. So we no longer have to provision physical servers or platform as a service products. Instead, we just can focus on our code. We can build and work the exact way we want to. It gives us an instant and event-driven architecture that is almost infinitely scalable. It allows our components of our application to react to events happening within our wider infrastructure. These events could be something like a timer trigger, a webhook, or watching for an event on a queue. And crucially, you only have to pay for what you use. So we are billed on a per execution and based on the amount of compute that gets consumed. This gives us a lot more flexibility with regards to scaling. All in, this brings a reduced amount of DevOps and DevOps overhead and a faster time to market because we can just get our code out there and just have to focus on code and not on infrastructure. So there are a couple of key characteristics that we really need to understand, as I explained a minute ago, generally, serverless is following an event-driven system that allows your code to react to events happening within your wider application. It allows us to scale from 0 all the way up to what we need and all the way back down seamlessly without having to manage any infrastructure or overheads. You pay for exactly what you use. So if you do scale, you pay for the amount of compute that's needed, but you can also pay nothing if you don't need to be scaled up or be running at all. And it's critically completely managed infrastructure. This brings an increased elasticity, but also much more cost effectiveness. So you can effectively seamlessly execute your workloads on the cloud without having to worry too much about the underlying infrastructure. Those workloads could be anything from AI to new apps or modernizing your existing ones by taking your existing code and placing that on a serverless platform. You're focusing more on code, on the scalability, and critically getting cost efficiency as a result. So within Azure, we have a sort of application hosting continuum, a spectrum that you could decide to host your application on. This is everything from virtual machines to all the way down to low-code solutions. Critically, the differences here kind of vary based on the level of control that you get. So, of course, with virtual machines, you have full control over the actual underlying infrastructure. With containers and that sort of setup, you have that abstracted away, and it makes scaling a lot easier. You focus more on deploying your application and how the application scales. PaaS and serverless gives you the sort of, the kind of fully managed environment, and low code gives you, everything. It manages everything for you. In the Azure space, when we're talking about PaaS and serverless, this is typically products such as Azure Functions or Azure Container Apps or Azure Application Service. Within the Azure environment, of course, you've then got a whole host of other services that underpin all of these, and you can integrate with them. So things like the Azure OpenAI service or the Azure AI Studios and machine learning tools. You've equally got managed database services like Azure SQL and Cosmos DB, and of course, a full suite of DevOps tools there as well, from GitHub to VS Code to Azure DevOps. Really, this is all about improving scalability and agility within the cloud. So you have a choice really here of what you decide to work with.
Cool, thanks, Callum. So Azure Container Apps is a serverless containers compute platform that allows customers to build and deploy cloud-native web apps and microservices. And it makes it easy to deploy your apps without any prior knowledge of containers or Docker files. And it has built-in event-driven scaling and scale to zero capabilities for your containerized apps. And because of this, it also offers a pay-per-use billing model. So you only pay for resources when they're actually serving a response or a request to your customer. Now, Container Apps is built on the foundations of open source components. We don't hide the fact that it's built on top of Kubernetes, but it weaves in default open best practices with popular CNCF projects like Dapper, the Distributed Application Runtime, and KEDA, the Kubernetes Event-Driven Autoscaler. And Container Apps allows you to build a variety of apps ranging from microservice architectures to containerized web apps, from event-driven apps through to web, IoT, and mobile backends, and all the way through to AI-driven intelligent applications. And Container Apps is well equipped to support all of your intelligent app needs with the ability to run as apps, jobs, and add-ons. Now, apps are services that run continuously. So if one of your containerized apps fails, it's automatically restarted, helping make your application highly available and highly reliable. Jobs are tasks that start, run for a finite duration, or complete a specific thing, and then exit when finished. They can be invoked on demand, they can be scheduled like a cron job, or they can be event-driven. And add-ons allow you to run vector databases like Quadrant, Milvus, and Weaviate, all powered on the same serverless compute platform that's running your containerized applications. One of the challenges that we see with intelligent apps is that large language models, or LLMs, can't solve computational problems directly, things like mathematics. However, LLMs can generate code, like Python code, to solve those sorts of problems. And so when your intelligent app needs to solve a computational problem, it can generate and execute the code, and then it can respond with a mathematically accurate solution using natural language, giving you the best of both worlds. However, LLM-generated code doesn't go through any sort of governance checks. There's just no way it could be checked in the time without slowing down your app. And therefore, it must be treated as untrusted code, and therefore it must run in an isolated execution sandbox. Those sandboxes can't interfere with each other, they can't interact with each other, and there must be no way of data passing between those environments. But these sandboxes have to start up really quickly and be really performant. They have to run and return the results really quickly so that they don't make the main intelligent application feel slow or laggy to the customer. The platform that would provide these sandboxes also needs lifecycle management. You're going to have to create and destroy a large number of these sandboxes over time. And both the sandboxes and the platform running them also needs to be highly scalable. We're going to want to run thousands of sandboxes for each of our apps over time. So as I mentioned previously, there are currently 3 resource types that we have in Azure Container apps, jobs, and add-ons. But I'm happy to announce a new resource type called dynamic sessions, which allows you to run isolated sandboxes for executing untrusted code at large scale. So let's have a quick look at how dynamic sessions addresses each of the security concerns we talked about just now. So each sandbox is run inside its own Hyper-V isolated boundary, and there's no way for these sandboxes to interact with each other or interfere with each other. You can run code in just a few milliseconds. If you don't have a session already, then dynamic sessions will allocate you one, and it will be available and running your code within just a few milliseconds. It will also automatically delete sessions once they're idle, so you don't have to worry about any of the lifecycle management concerns. You can set a TTL to define how long an idle session hangs around before it's deleted, and then let dynamic sessions and container apps take care of the rest. And dynamic sessions is super scalable. We're already using it internally in some Microsoft products, and we're running millions of sessions per day using this feature. Now, dynamic sessions will be available in 2 modes. The first is code interpreter mode. This has a built-in Python execution environment that comes with many Python libraries pre-installed. And this Python image is fully managed by Microsoft, which means customers don't need to know about containers to use it. They can just get started. And this uses the consumption-based pricing model, with costing just 3 cents per session hour to use. We're also going to offer a custom container mode where customers can bring their own container image and they can run pretty much anything they want. So maybe you want to run your LLM code in a different execution environment that's not Python. Or maybe you want to do something totally different, like running a cloud-based IDE service like GitHub Codespaces. You can do that with a custom container. And back to you, Callum, to talk about some of the features and announcements for Azure Functions.
Fantastic. Thanks, Paul. That looks really awesome. So the other feather in the Azure serverless bow is Azure Functions. This is a product that, as I mentioned earlier, allows you to build event-driven applications in a serverless fashion that scale end-to-end without you really needing to do anything. So this allows you to deploy multiple application types with languages ranging from C# to PowerShell to JavaScript and beyond. You can deploy applications in a containerized environment, effectively microservices, and they all share a common underlying runtime, the Azure Functions runtime. One of the critical differences with Azure Functions is its programming model. So it's using an event-driven model that has a concept of triggers and bindings. Triggers are something that causes the code to execute, and a binding is a data source that you might map to your function when it executes. An example of this could be a trigger being an HTTP endpoint that gets requested. It could be watching a queue for new items that are added, or it could be a timer. A binding might be, for example, binding to the Azure OpenAI service, so you can easily interact with an LLM. I mentioned already that this gives you this seamless end-to-end scaling, and therefore you don't need to worry so much about infrastructure, thus improving the developer experience massively. And of course, we're excited to talk today about the new Azure functions on Azure Container Apps, which has become generally available. This effectively allows you to deploy your Azure functions onto the Azure Container Apps environment. So if you already have other applications running in Container Apps, but want to take advantage of this event-driven programming model, this is a fantastic option for you to do so. Okay, I mentioned we've got a few triggers and bindings, but let's talk about some actual use cases where this could be used in the real world. Of course, if you're building a mobile application or a web application, then having a serverless backend is a fantastic option where you don't need to provision dedicated infrastructure, and you can only serve your requests as and when it's needed. For something like a static website where you may have a contact form, this is perfect. Or a progressive web app that could be used offline, but then may need to sync back to the cloud periodically. It's also good for things like real-time data processing or stream processing, where you need to ingress data that's coming from, from a platform. You queue it up and then you process that maybe in batches. Functions means you're not provisioning infrastructure that sits there waiting for data all the time. It only reacts as and when it's needed. For things like workflow orchestration, this is perfect for a sort of fire and forget event that happens, and equally scheduled tasks that happen once a day, where perhaps you need to do database operations, reporting, or cleaning up things in your system. If you're building IoT or doing any edge compute, having a connected backend service like Azure Functions is great, because it means you can offload your workloads to the cloud again as and when you need. And finally, when we're building intelligent apps for things like fraud detection, risk analysis, and just general LLM integrations for building RAG applications, etc., Azure Functions is perfect. So until now, whenever you need to use Azure Functions, you pay for the amount of resource that you use, and each new request and each new execution is 1 unit of compute. Well, today we're excited to talk about the new Flex consumption plan, which lets you control the concurrency that your app handles, meaning the number of requests, number of executions that each instance of your function running can handle by default. There's sensible defaults in place for most use cases, and they make sense. So you probably don't need to change them, but you can if you want. Scaling on the Flex consumption plan is therefore driven by concurrency and also the event source length. So when we're talking about an event source here, we mean the trigger. If your trigger has a queue and you've set your concurrency to be 2 items, well, then it will scale based on the number of items in your queue. Here's an example here of how this looks currently. So if I had 10 HTTP requests hitting an Azure function with an HTTP trigger, what that will do is it will spin up 10 underlying executions of my function, meaning I'm paying for 10 executions of that function. Whereas on the Flex consumption plan, there is now the option to configure the concurrency. So that same 10 HTTP requests with a concurrency of 2 means I'm only paying for 5 executions under the hood, 5 times the amount of compute. What this effectively means is I can either double my throughput or halve my costs, because I'm able to handle the same amount of traffic with half the amount of underlying compute. There's also some newly announced exciting Azure OpenAI triggers and bindings. This is perfect if you're trying to build intelligent applications with Azure Functions. So this is perfect for things like RAG workloads, where you're going to interact with external search systems like Cosmos DB or MongoDB, or even Azure AI Search. It's completely configurable and pluggable. So with literally a single line of code, you can interact with one of these external services for your RAG contexts. And then it makes building things like chat and OpenAI based assistants super easy because it's integrated exactly with Azure Functions. Your code can execute when a certain event happens and then call straight off to the Azure OpenAI service without you needing to interact with their APIs directly. Now we're going to talk about another important aspect of building a future-proof application in the cloud, and that is Azure API Management. So what is Azure API Management? Well, Azure API Management is a suite of tools that gives you a gateway for your application. It comprises of things like, I mentioned the gateway, but also a management plane for your public endpoints, and also a portal for handling all of your different backends. So this is great if you're building an application at scale. It allows you to put a gateway in front of your application and internally route that traffic to wherever is most appropriate. That could be different backend services, different Azure services, or different APIs. One of these cool new features is the Azure API Center, which has just entered general availability. This gives you one centralized place, one centralized inventory for managing all of your API endpoints and your connected backend services. This means you're able to view in one place all of the different services you integrated with. It could be an Azure function, could be an API hosted on container apps or AKS automatic, like Paul showed you earlier, or it could equally be an endpoint talking straight to, say, the Azure OpenAI service. It gives you one friendly place where you can control all of this. Now, when we're building an intelligent application, it's really important to have a gateway, especially when it comes to scaling. So in my example here, I've built an intelligent mobile application, and that talks directly to my Azure OpenAI endpoint. That has my Azure OpenAI keys, etc., shared, and they're embedded directly within my intelligent app. If we go to the next stage, we can see when we scale up our application that this becomes slightly problematic. Now, multiple applications are talking straight back to that same Azure OpenAI endpoint, meaning my quotas, my resources are burned far quicker. It also means that my OpenAI keys are now distributed across more devices. It's not ideal. This is where the application gateway comes in handy. So if we can put an application gateway in the middle of these requests, it allows us to internally route the traffic back to the Azure OpenAI service. It also allows us to do things like tracking token usage, to configure multiple endpoints that are multiple OpenAI endpoints or service endpoints in the background, handle authentication and authorization based on the gateway and not having that set on device, and also enforce fair use limits for users for certain endpoints, so a token-based limit, for example. So today, we're excited to talk about the Azure OpenAI policies for Azure API Management. This gives you far more control over how you would interact with the OpenAI service with Azure OpenAI API Management. So the first example of this is a new Azure OpenAI token metric policy. This allows you to, within the gateway, configure a policy that you can siphon off telemetrics and logging based on the requests that are being made through your system to the Azure OpenAI backend. You can store all of the metrics in something like Azure Application Insights, and it's configurable with a couple of lines of XML in the policy configuration for Azure API Management. Another exciting feature is this new Azure OpenAI token limit policy, which allows you to configure the number of requests that should be hitting your backend, effectively the throughput to your backend service. In this example, we've got 5 requests coming in, but the token limit policy filters out anything that physically can't be serviced by that backend within our configured token limit. So in this case, 1,000 tokens per minute. It's a great example of a way of preventing your backend services from being swamped by too many requests. Another, and I would argue my favorite new policy, is the Azure OpenAI semantic caching policy. When we're talking about building intelligent applications that are interacting with an LLM, every single request is unique because people are talking to the model in natural language, and that changes. It makes it very, very hard to cache. What the semantic caching policy lets you do is configure a threshold where within a certain range, you would consider a certain set of tokens the same as another set of tokens, and therefore you could cache that request reliably. You can say this these two queries were the same. They're within, in our case, a 0.05 or 5% threshold of each other, and therefore we want to cache these. You can then configure this with something like the Azure Cache for Redis service to prevent requests going to your backend service unnecessarily, and they would therefore be served directly from the cache. And finally, a feature that has become generally available is the load balancer and circuit breaker policies in the Azure API Management. This makes load balancing much more of a reality, especially between multiple backend Azure OpenAI endpoints. In this example, let's say we've got a primary and a secondary instance of Azure OpenAI, and for whatever reason, we want to distribute our traffic between them. It could be that one of our backends becomes available, and we want to make sure we can fail over to another region where the application is still available. Or it could simply be a way of limiting your resource consumption across multiple regions, perhaps across multiple billing models as well. In this example, you configure it so that a certain number of failed requests or a certain number of timeout requests to a backend effectively treat that backend as unavailable, and the circuit breaker kicks in. It automatically takes that backend out of the load balancing pool and distributes other traffic to the secondary backend. Equally, it could be that backend service responds with a token limit exceeded response saying, hey, I've reached my limits. Therefore, you can configure the circuit breaker to kick in and fall back to the other region. So the service is still available, but it's just not suitable for serving traffic anymore. And I have a quick video that demonstrates this as an example. So in this video, we have a Python application that's going to call an endpoint in Azure API Management. And that has two OpenAI backends configured. These have token limits set, where my Canada East region can serve effectively 100 tokens, and my East US region serves everything else. Once the Canada region limit is hit, you can see how it automatically fails back over to the East US region. This allows us to evenly load balance our traffic across different regions and reliably bake in this circuit breaker functionality. Okay, so we showed you some big blobs of XML there, and I don't know about you, but I personally don't like writing big blobs of XML, and it's equally difficult to understand sometimes what's going on here. Well, the Copilot for Azure API Management tool, which is now in preview, helps with this. It allows you to understand exactly what a given policy and the XML for that policy is doing and how you could configure it. So you don't need to worry so much about configuring these yourself. You can ask Copilot in Azure API Management, and it will guide you to the right place to configure these policies for caching, etc., and help you scale your intelligent applications.
Cool, thanks, Callum. Some great new features there. Really excited to hear about them. So just before we close today, we wanted to quickly run through a few key takeaways that we hope you picked up on. The first is that AKS Automatic provides a new experience for AKS that helps you create and manage production-ready clusters with minimal effort and with best practices baked right in. And this will help you focus on developing and running your applications whilst letting AKS handle the rest for you. And whilst automatic is a more opinionated and automated mode of operation, it's still AKS, and it still provides you the full power and flexibility of the Kubernetes API and access to the ecosystem when you need it. And if you find that the AKS automatic approach doesn't work for you, you can easily switch your cluster to an AKS standard cluster. And this won't impact your applications or otherwise affect your environment. And dynamic sessions for Azure Container Apps allows you to quickly and easily run sandboxed execution environments, which allows you to execute untrusted code at huge scale. We provide a fully managed Python environment to get you up and running really quickly, and dynamic sessions will manage the life cycle of these execution sandboxes so that you don't have to worry about it.
And flex consumption with for Azure Functions or Azure Container Apps Azure Functions on Azure Container Apps is the key really to delivering scalable and building scalable event-driven applications in any language. The new flex consumption plans give you a lot more control over how the actual compute is used and how your scaling happens with the new concurrency features. Azure API Management is essential when you're looking at scaling and securing any cloud application, but especially intelligent applications where you don't want to be exposing your credentials publicly, and you want to be able to put things like circuit breakers and caching policies in place, which are helped by some of the new OpenAI policies that have been introduced, and they solve these challenges for you, things like caching, load balancing, etc., for intelligent apps. And of course, a quick shout out to the Copilot for Azure API Management, which helps you configure all of this without needing to understand necessarily the exact syntax.
Cool. So thank you very much for joining us today. We hope you found this session interesting. If you have any questions, please do reach out through the reactor, and have a great rest of your day.
Thanks, everybody.
Thank you.